Welcome to EE 544 on Tuesday, February 11, 2014.
Good afternoon, everybody. Okay, let's continue our discussion from last time, try to wrap up the material on the nonlinearity and distortion. And again, as I told you last time, the nonlinearity causes different types of distortion, including the harmonic distortion. We already talked about this. And the intermodulation distortion. Intermodulation, we have two types, the second order intermodulation and the third order intermodulation. We also looked at the intercept point, the IIP3 and the OIP3, and how we calculate the IIP3 or the OIP3 for the entire receiver chain. And we also found a different, some of you send me the derivation. I will grade it tonight. I did not have a chance yet to grade it, so be patient with me. I will grade the thing that you send me in regard to the equations in the chart. Clear? Which is the relative, the relationship between all of these parameters. Clear? No response. Clear? Okay, we did this one last time. So I think we ran out of time here. Which is what? Which is the 1 dB compression point. We need to understand what is the 1 dB compression point. First of all, let's see the graph so that from the graph we can get the idea about the 1 dB compression point. This is it. Yes? This is the what? This is, don't worry about this. This is for the third harmonic. Third intermodulation. Concentrate on this. This is for the fundamental. You can see that the graph has what? Deviated from the linear side. The point in which the power difference between the linear and the actual curve is 1 dB. That is what is known as a what? The compression point. The question is what? Why is this one compressing? Why is this one compressing? Notice, by the way, in reality, this one will what? Saturate, and after with that, it might even go what? Go down. Are you following me or not? Clear? Okay, keep that in mind. Now, let's understand the equations. We consider a single tone. Assume that we do have a single tone excitation. So the input is what? The input is VI equal to what? VI of t equal to what? VI cosine omega t or omega naught t. That's the input. Yes? The system is introducing what? Nonlinearity. Yes? So what do I get? I get C naught plus what? C1 VI cosine omega naught t or cosine omega t plus what? C2 VI squared. This is from what? The second order nonlinearity. This one is from what? Third order. Clear? Single tone. Are you following me on that? Okay. Now, what do I need? What do I have? I simplify this. From this, am I going to get the fundamental? I'm not going to get the fundamental. From this, am I going to get the fundamental? So what is the fundamental? Concentrate only on the fundamental. What is it? C1 plus what? C3 VI square over what? 4 times what? VI. Did you answer where this came from? Yes or no? What is the first term? One more time. C1 VI, which is this term. And the second term is what? C3 VI. There's a square here and there's VI here. Yes or no? Divide by 4. Clear? What 3? That's the 3. Sorry. 3. I'm sorry. 3. Corrected, please, corrected. There is a 3 missing here. That's the 3 is from this term. Clear so far or not? What is the gain? What is the gain of the amplifier at the fundamental? It's what? This divided by what? This. Do you agree? The VI cancels. So what do I end up? This one does not look clear in the diagram. So what do you end up with? C1 plus is 3 VI square over what? Or times what? C3. Did you get it? This one is equal to. Did you answer where this came from? Where this came from? Dividing what? This, which is the voltage at the what? At the fundamental, at the output divided by what? This, which is the input. The VI cancels and you end up with this. Now, what is the problem with this? The problem with this is that if C3 becomes what? Negative, you are going to get what? See, if everything is ideal, If everything is ideal, what should the gain be? What should the voltage gain be? The voltage gain should be what? C1. You agree? C1, which is this term. But because of the nonlinearity, we are getting this term. And if C3 becomes what? Negative, then this one will actually what? Will actually giving you what? Giving you the compression stuff. Clear? Now, how do I get the 1 dB compression? How do I get the 1 dB compression? Hold your question for 1 minute. How do I get the 1 dB compression? Let's see if you can help me. This the 1 dB compression again is the power level at which the gain at the fundamental frequency is reduced by what? 1 dB from the what? From the linear. So what do I do? Let's see if you can help me. Concentrate on this side. Concentrate on this side. What do I have? What is the gain if it is linear? If it is linear, C1 times what? VI, the output voltage. Yes? Why is it 20? Because this is a what? A voltage. Did you understand that or not? So it's what? 20 log C1 VI minus what? 1 dB. Yes? Equal to what? 20 log C1 VI plus what? 3/4 C3 VI cube. Did you get this or not? Yeah, what is this? One more time. What is this? This is the output voltage. Yes? The output voltage at the fundamental. What is this? This is the output voltage at the fundamental, assuming what? Linearity. So I'm subtracting what? 1 dB from it. Did you follow me or not? 20 log. Now, then you what? Then you remove the logs in here. So what do you get? From this equation, you get what? 1 plus this one. Bring this one to this side. Yes or no? Yes or no? 1 plus 4 over 3 over 4. C3 over what? C1. All of this is missing. VI square equal to what? Equal to 0.89. Yes or no? Okay, 0.89 is from this term here. Yes? Which means what? VI. Why is this one not clear? VI, the 1 dB, is what? Is 0.145 times what? The absolute value of what? C1 over what? C3. Clear? Clear? Now, if you compare this with the power, with the 1 dB compression power, minus this, plus this, which is what? Which is the 10 log, point what? 145 this. Yes? Why is it now 10? A square root. Yes or no? So when you multiply 20 log times what square root, it becomes what? 10 minus the what? IP3. What is this, by the way? Can you tell me what is this? This one we found it last time. Let's see if you remember. Do you remember this equation? Yes or no? What is this? VIIP3. What is it? That's the input voltage. The input voltage when what? When the fundamental power and the what? Third order intermodulation power intersect together. That's the input voltage. Yes? I want you to see this, and I want you to see this. Is there a similarity? Look at this, and look at this. This is the 1 dB. This is the voltage at which what? 1 dB compression occur. This is the what? The voltage when what? When the fundamental and the what? The third order intermodulation are what? Power are what? The same. It's just this constant is different. Do you agree with me or not? Both of them has what? Absolute value of C1 over what? C3. So if I subtract one from the other, yes or no? Cannot hear you. This is what I get. What is it? P1 dB, which is what? Which is the 1 dB compression power is equal to what? IIP3 minus what? 9.6 dB. What does that tell you? It tells you roughly, the what? The IIP3 is 110 dB more than the what? Compression point, which means what? Roughly, which means what? This, where is the IIP3? This is the IIP3, yes? And this is the what? 1 dB compression point. Roughly the difference between them is roughly what? The 10 dB. Which one is higher? The IIP3 is higher by roughly what? 10 dB. Did you answer where the 9.6 came from? 9.6 came from this constant here. This one and this one. Yes or no? Okay. Did you understand where the 3/4 came? This 3/4 is the what? Is the inverse of this one. Why? Because I'm subtracting. Yes? So the denominator becomes what? The numerator, numerator becomes denominator. Clear? Clear? Question? I did not get your question. The what? This C sub 1 and C sub 3 depends on what? The components itself of the amplifier. Which one? C1 and C3? No, not on the input voltages, but it depends on the components. The input voltage is here. This is VI square. The C1 and the C3? C1 and the C3 depends on the circuit itself, not the input voltage. It depends on your amplifier, the components of your amplifier. Are you following me on that? Look, listen to me. If you do have a device, and that device is what? A nonlinear device. Where the nonlinearity came from? It came from the components, a transistor, or a MOSFET, or a diode. Are you following me on that? Has nothing to do with what? How much voltage you are applying in. Clear? When you apply a voltage, if the voltage is small, it means that you are operating in what? In the linear region. But as you increase the voltage, the input voltage, what will happen is what? What happen is that this one will what? Will saturate. Why? Because of this term. Did you understand that or not? C1 and the C3 has nothing to do with the input voltage, but the input voltage does have an effect on what? On the compression. Because of which term? Because of this term. Clear? Clear? Okay, good. Now, so this is the 1 dB compression point. Notice, by the way, if there are higher order nonlinearity, tell me, will the 1 dB compression change? Why? Because, by the way, the fundamental will come only from which type of nonlinearity? The fundamental. Did it come, the odd nonlinear, did it come from here? Does the fundamental come from here? Does it come from the 4th order nonlinearity? It only comes from what? The odd order. So the more odd order you take, this one will what? This one will what? Change. Did you get my point or not? Yes or no? But will this one change? IP2 and IP3. IP2 and IP3 will not what? Will not change. Are you following on it? Because IP3 we are talking about what? 3rd order intermodulation. Clear? Higher order will give you what? What will give you? If you take, for example, the 5th order, what will give you? It will give you the what? The 5th order intermodulation component, not the 3rd order intermodulation. Not sure you are getting this. Are you getting this or not? Yes or no? Not sure. When you take higher order, are you going to get, what is the 3rd harmonic? Sorry, 3rd intermodulation. What is it? 2F2 minus F1, 2F1 minus F2, 2F2 plus F1, the last one, 2F2, whatever, minus F1. Yes? This will come only when you what? When you do have the power to the what? To the 3. You agree? If it is power to the 5th, what are you going to get? You are going to get 5th order intermodulation. Yes or no? Yes or no? But this is what we are talking about, IP2 or what? IP3. Clear? These are the 3rd order intermodulation. Clear? Okay, good. Now, one more thing to look at, which is what? Which is a strong blocker. What does it mean? Let's see if you can help me here with a strong blocker. Where is the signal here? Can you show me where is the signal? Where is the signal here? The desired signal. The desired signal is what? Is this one. Do you see a peak? Here. Can you zoom in, please, a little bit? Operator. Hey, very good. Very good zooming. This is not only very good zooming, but it is what? Fast zooming. Fast zooming. You see this peak? This one. By the way, what is this? This background noise. But do you see a peak here? That peak is the desired signal. What in the world is this? That is an interferer that happens to be what? Close by. Yes? It is much stronger than the signal. Let's see what happens. Let's see what happens. So what do I have the input? The input is a what? It's the desired signal, which is what? VD. D is the desire. Cosine omega 2t. Yes or no? And the blocker is what? VB. Now what do you notice? Is it the same frequency or is it different frequency? Different frequency. By the way, if it is the same frequency, this one is what? Dead on arrival. Did you understand that or not? Cannot hear you. This is what kind of interference? This is adjacent channel rather than a what? Co-channel. If this is co-channel, this one is dead. It does not have any what? Any opportunity of survival. Did you get, if this is it? Did you get my point or not? Okay. Now, apply this. Can you zoom back, please? Thank you. Apply it to the what? Nonlinearity. Apply this, the sum of these, to the nonlinearity. Yes? What do you notice? What do you notice? You notice, first of all, now let's assume the nonlinearity is what? Let's assume that we are dealing with what? With the third order nonlinearity. By the way, the second order terms, what does it generate? Second order means what? Means this one is what? Square. What is it generating? It's generating second order harmonic distortion. Yes? Generate what? Intermodulation, second order. And it also generate what? DC. Clear? Okay. All of these result in what? No problem if we are using what? The super heterodyne receiver architecture. Do you agree? Agree or not? They will not cause me any problem. Clear? Okay. The problem comes from where? From the cubic nonlinearity, which is what? The C3 VI cube. That term in the output, in the nonlinearity. One more time. What is C naught? What is V naught? C naught. Plus what? This term. Are you following me or not? What will it give me? Let's see what it will get me. So VI cube, forget about the C3 for just a second. VI cube, because it's proportional to what? VI cube. What will it give me? Help me. VB cube, cosine cube, omega 1t. Yes? Plus what? VD cube, cosine cube, omega 2t. Yes or no? Where are these terms coming from? This one is what? Is the middle term, because you are multiplying it by what? Cube. Yes? This is one middle term. This is another middle term. Generates term at what? Omega 1 and what? Omega 2. Why at omega 1? Can you tell me why at omega 1? At omega 1, because this one is what? Cosine square. Cosine square is what? 1/2 plus what? 1/2 of cosine twice. Yes? The 1/2 with this will generate what? Will generate a term at what? Omega 1. Yes or no? And then, where is the omega 2? Omega 2 will come from this term. Yes or no? Along with what? Along with the intermodulation component. Clear? Clear? Okay. Now, the third term, these are two terms. The third term, what is the third term? The third term is much smaller than the last one. Which one? You see this one here? This is VD cube. Remember, VD is what? It's very small to begin with. Are you following me or not? Okay. I want you to tell me, I want you to look at this, and I want you to look at this. Which one is more damaging? This one or this one? This one is more damaging. So, why? Because VD, I'm sorry. I got them backward. This one is more damaging. Why? Because VB is much higher than VD. This one is what? Is VD square VB, whereas this one is what? VB square VD. Did you get this or not? This is much more damaging than this one. Yes? Clear? Oh, now let's understand what will happen. The blocker terms comes from the last term, and it is given by what? By this term. Why do I say blocker? I'm still not sure that you got this term. Where is this term coming from? This term, which is the one that is causing me the trouble. Why is this one causing me the trouble? Because it's at which frequency? Omega 2, which is the same as what? The desired, which means this one is acting as a what? A co-channel interference. You lost me. I can tell you lost me. Can you go back to the previous page? Concentrate on this term. This term is negligible. Agree? Okay, so what do I have here? Listen to me. 3 VB square BD cosine square omega 1t. What is the cosine square omega 1t? It's 1/2 plus this. I want you to see this term. 3/2 VB square VD times what? Cosine omega 2t. Yes? At what frequency is this term? It's the desired frequency, which is omega 2. It's not on omega 1 anymore. Are you following? Where was the interferer? At which frequency was the interferer? Omega 1. But because of the nonlinearity, you will get a term at what omega? Omega 2. At an amplitude of how much? 3/2. Yes? C3 VB square. Is this large? This is large. VB square times what? BD cosine omega 2t. Yes or no? Now, what is the gain will be? At which frequency? The gain at which frequency? At omega 2, which is the desired one. Yes? What is it? Tell me where is this term came from? C1 VD. Where is it? That's from the linear component when the input is this guy. Yes or no? So what is this? This VD is what? Is the amplitude of the what? Of the input at the fundamental. What fundamental? Omega 2. Where is this coming from? Explain this one coming from where? C1 VD. This one is what? Is the linear part at what frequency? At omega 2 for the desired. And what is this? This one is this term, which is what? 3/2 C3 VB square times what? BD. Clear? Clear? It's this term. Now, if C3 is less than C1, if this C3 is less than C1, sorry, C3 over C1, I'm sorry, C3 over C1 is what? Negative, which means what? C3 is what? Negative. By the way, could C1 be negative? Why? Couldn't there be an amplifier that introduced 180-degree phase shift? C1 also could be a negative. I'm not sure, did you get my point? Could you design an amplifier that will amplify the signal but introduces a what? 180-degree phase shift. You could do that. Are you following me or not? Okay. If C3 over C1 is negative, what will happen? The blocker term, this is the blocker term, will subtract from the what? The desired term. That reduction due to the blocker does not require that the blocker be what? In band. I'm not sure, did you get this point? Did you get this point here? Yeah, what is this point? What is this point is saying? This omega 1, where is it? This omega 1 could be what? Out of band. Are you following me or not? It could be out of band, but because of the nonlinearity, it resulted in what? In an interference term, which is what? In band. Actually, not only in band, but it's at the same what? At the same frequency. Yes. That's the point. So the gentleman's question is what? Then we need to make sure that the out of band is what? Is properly attenuated before you go to the first amplifier in your receiver chain. You follow me or not? Why? Because if there is one that is still there or that leaks through that duplexer to the input of the amplifier And if the amplifier has no linearity, it will result in what? It will result in blocking of your receiver. First of all, do you understand what a blocking of a receiver means? Blocking? He is not going to be able to what? To recognize there is a what? There is a desired signal. Why? Because the amplifier is no longer an a what? An amplifier. It's now a what? A compressor. Are you following me on that? And the desired signal is weak to begin with. So if you compress it, it will become even what? Even will become weaker.
How can we get rid of the blocker? The blocker is inside the band.
No, by the way, if the blocker is inside the band, the situation even become what? Worse. And this one is telling you what? You will still get a blocking even if the blocker is what? Out of band. If it is in band, it is problematic. Why? Because it's not going to be filtered out from the band select filter. I'm not sure, did you get this statement? This statement tells you what? Even if the blocker was out of band, you will still have a what? A problem if the blocker happens to be what? Strong blocker happens to be what? Nearby. You will not. I just told you, if it is in band, you can only what? When you go to the what? To the band selection filter, or the what? Or the image rejection. Remember the image rejection? You use it what? A narrow band so that the image is what? So that the interference which happens to be close by get what? Get attenuated. Are you following me on that? Clear? The in-band is always a problem. The in-band is always a problem. You need to deal with it. Clear? Here he is telling you, or the statement is telling you that even if the blocker happens to be out of band, it still can result in terms which are what? In band. Or even what? At the same frequency. Clear? Okay, good. Now, this is just an example, numerical example. And again, as you will see something like this in the midterm. I will call the section cookies. Cookies means what? It means that you need to know, by the way, all of these equations. I don't want you to memorize any one of these equations. All of these equations will be with you in the midterm. The question is what? You need to figure out which one to choose, which one to use. Clear? Okay. So calculate the blocker level that will reduce the gain. Reducing the gain means what? Desensitizing. Desensitizing. Yes? Yeah. What is sensitivity? When we talk about sensitivity, what is it? It's the ability of the receiver to detect weak signals or strong signals. Weak signals. So desensitization, it means what? You are reducing that level even lower. Are you following or not? By what? 3 dB. What do I do? This one is the what? We just calculated this, which is what? This term. So it's what? 20 log. Why is it 20? So it's the voltage. Yes? 20 log 1 plus 3 over 2. This is the gain. Do you agree with me or not? Remember, without it, what was the gain? Without this, what is the gain? C1. With the gain is what? Is this term. So you say what? 20 log this term is equal to what? Minus 3 dB. Are you following me or not? From here, what do you get? You get the value of BB, and from the BB, you can get what? You get the blocker. The output blocker is what? Is 1 dB, the compression point, plus what? 1.2 dB. What does this mean? What does it mean? It means the blocker power is more than the what? The 1 dB point by roughly what? 1.2 dB. 1.2 dB is very little. You agree? Which means what? Once you reach the 1 dB compression point, the blocker becomes what? Becomes serious. Why does it become serious? Because the characteristic of the amplifier will exhibit the what? The nonlinearity. Before that, we don't have that problem. Do we have that problem before that? I don't know where I put it. Before the 1 dB compression point, do we have a problem with nonlinearity? We don't have a problem with the nonlinearity. Yes? So if we do have a blocker, yes? By the way, if it is out of band, we already got rid of it from where? From the band selection filter. Clear? The problem comes what? Comes when this one gets what? Closer to the what? 1 dB compression point. I want you to see, this is the 1 dB compression point. You agree? Yes or no? Okay. How much was the compression? only but 1 dB. You agree? Afterwards, it becomes even what? Much higher. Than who? Than who? The linear. Look at what is at this point. For example, at this point, what is it? It's this. At this point, it's what? This. This. Are you following me or not? The difference between what? The actual linear and the what? The compressed. Are you following me or not? This equation tells you what? It tells you that if it exceeds by roughly 1 dB, the 1 dB point, it becomes what? It becomes a problem of the blocking. Clear? The B stands for block. So avoid operating the amplifier near the what? The 1 dB compression point. In addition to the above, remember there are considerable IM distortion close to that what? To that point. Are you following? So in addition to the blocking problem, we have what? The third order intermodulation. Are you following me or not? So what this statement tells you what? Avoid operating at what? At this point. Because when you operate at this point, you have two problems. The blocking and the what? The intermodulation. Yeah. But the problem is that when you operate down in here, the efficiency will suffer. Are you following me or not? Because you are not using the what? The gain of the amplifier properly. Clear? Okay, good. Now, we'll talk about this later on when we get to the actual amplifier design and so on and so forth. Now, one more parameter to talk about, which is what? The dynamic range. The dynamic range. Now, we do have two types of dynamic range definition. The first one is called what? The linear dynamic range. And the other one is called what? The linear dynamic range is this one. The other one, we call it what? The spurious-free dynamic range. Both of these are used in the industry. So I need you to understand the difference between them. Okay. I want you to see this. Tell me, what is this? That's the noise level. Are you following me? By the way, shortly we will see that the minimum detectable signal, which is MDS, is very close to the what? Noise level. It's a little bit higher than what? Than the noise level. This is a background noise. You expect always that there is a what? Background noise. Are you following me or not? From what? The environment and so on and so forth. The MDS will be just a little bit higher than this. Clear? Okay, what is this value? What is this value? It's the 1 dB compression point. The difference between what? The difference between the 1 dB compression point and the what? And the minimum detectable signal, or approximately the what? The noise level. Yes? Or if you want to call it what? Sensitivity. It's what is known as what? The linear dynamic range. Clear? No response. Clear? Measured in what? Is it power or is it dB? It's dB. It's a ratio. Are you following me or not? It's a ratio. And this dynamic range, by the way, can be measured based on what? Based on the input from the input side, or measured at what? At the output side. Are you following me or not? Either in the input side or the what? Output side. Same thing. Did you get this or not? Because it's a ratio. Yes or no? I'm not sure. Did you get this? Did you get this or not? Does it matter, the ratio? If you look at the input side or if you are looking at the output side, does it matter? It's the same ratio. It will cancel from the numerator and the denominator. Yes? Okay. Now, what is the spurious-free dynamic range? What is the spurious-free dynamic range? Let's see if you can help me. This is the third order intermodulation. Yes? The point where it intersects the what? The noise floor. What does that mean? When it intersects the noise floor, the effect of the third order intermodulation becomes what? Significant or not significant? Not significant. And that is why we call it a what? Spurious. What is a spur? Unwanted signal. Not noise. Not noise. Noise is always there. A spur is an unwanted signal. Is a third order intermodulation. Is that a spur? That's a spur. When it reaches this point, it becomes what? Negligible. Do you agree? That is why they call it what? The spurious free. Negligible. The dynamic range, the spurious free dynamic range is what? Is from here to what? Here. Did you get my point or not? Yes or no? Which is what? Which is the difference between the fundamental what? The fundamental power, yes, and the power at which what? What is this? The power at which the third order intermodulation becomes the same as what? the noise power. We still need to figure out how we calculate the noise power. We'll get to that in a minute. Did you get this or not? Yes or no? Now, unfortunately, our author, who is Steer, not Trazavi, Steer book, mixes them up. He defines this one as the what? As the linear dynamic range, and this one is the what? The spurious free dynamic range. But because I think it's a typo. Did you get my point or not? So don't make that mistake. The linear dynamic range is higher than the what? The spurious free. Spurious free means what? You are not going to get any what? Intermodulation components. Clear? Negligible. Why? Because it's just like the noise level. Clear? Clear? Okay, you have to remember, there is always a noise level here. I don't know, remember or not, yesterday I broadcasted some answers to some questions from a student. Did you read this or not? You ignored it, you deleted. Did you delete it? You deleted, I can tell. And his question was the following. Can we use CDMA, what does CDMA stands for? Code division multiple access in every what? Cell. Because keep in mind, the CDMA, you are going to be transmitting at the same what? Frequency and at the same time, but using different what? Code. If you can use it in the next cell, it means the reuse factor, the frequency reuse factor is how much? 1. Is that good or bad? This is extremely good. Why? So that you don't waste what? Bandwidth. You can use the same frequency. But you have to always remember, as the number of users using the same frequency and at the same time, even though they use what? Different codes, the codes are orthogonal at what? At the point where they are transmitted. By the time they reach the receiver, they are no longer what? Orthogonal. CDMA uses spread spectrum, which means what? The spectrum is spread along what? Large range of what? Frequencies. Yes or no? If you keep adding users, this level, which is what? Spread along what? High range of frequencies, will keep what? Adding up to who? To the noise. Which means that is why in the answer I told him, eventually it will result in an unacceptable degradation to the signal to noise ratio. Why? Why is that? All of these interference is going to be added to the what? To the noise power. So the level of noise background will increase and the signal to noise ratio is not going to be what? Acceptable. Did you get my point or not? Yes or no? Which means what? When you hear talking about CDMA, you need to understand, in additional with CDMA, there is also what? FDMA. FDMA stands for what? Frequency division multiple access, which means what? Eventually you need to use a what? A different frequency. Just because the reuse factor is 1 does not mean that what? Everybody is going to use one frequency. Did you understand what I just said? Yes? Okay. But you will take that in the other class, I think. I'm not sure, but I think. The 535. But did you get the idea? Okay, good. Now, let's get to the noise. Any questions on the nonlinearity? Any questions on the nonlinearity? Okay, good. Now, let's get to noise. Let me first of all use the pad, and then I will get back to the charts. Noise modeling. Where is the noise coming from? Where is the noise coming from? By the way, this is this set of charts. This is set of charts. So make sure next time bring it with you. But I'm going to use the charts right now. I'm going to use the pad right now so that you get a better idea before we get to the chart. Where is it coming from? This noise. First of all, it could be what? Environmental. Outside, from the sun, from the environment. All of this is going to be manifested with what? With the antenna. The antenna will begin to what? Heat up. Are you following? And depending on the sun. And so most of the time, by the way, you see if this area is so hot, they will what? They will put somewhat shielding around the what? Antenna to protect it from the what? Heat. Because as we will see, as the temperature increases, the noise power will what? Increase as well. Are you following me on that? Noise, thermal noise is what? Results of what? Motion of electrons, random motion of electrons. And when electrons get what? Heated up, they get what? Real excited. Are you following me on that? They go crazy. Did you understand that or not? Oh, There are other types of noises that we referred to it earlier. There is what, for example, the flicker noise, the shot noise, and so on and so forth. All of these things. What we are going to be interested in this course, in this material, is the noise added what? Internally within the device itself. Are you following me or not? In addition to what? In addition to the antenna. Are you following me or not? In addition to the antenna. Now, first of all, let's understand what we're talking about. Now, keep in mind, theoretically speaking, a capacitor or an inductor will not provide you with what? With noise. Do you follow me or not? Theoretically speaking, which component will provide you with noise? Is the resistor that is going to cause the noises. Are you following me or not? So now let's understand how do we model it. This is a resistor. This is R. And this is a what? A noisy resistor. A noisy resistor. Clear? Clear? Now, notice, by the way, the noise is a random signal, which means what? I cannot describe it by an equation like I did for what? For the nonlinearity analysis, where I say what? Let the signal be what? A cosine omega naught t, A cosine omega 2t. Are you following me or not? I cannot do that. And here I need to deal with it in a what? In a statistical fashion. In other words, I talk about what? The average value of the noise. Or I talk about what? The mean square values of the noise. I cannot say what? Let's write an equation for the noise. Did you get this or not? Yes or no? I cannot deal that. I need to deal with it in what? Distribution. For example, I say what? This noise is what? Modeled as a Gaussian random variable. Clear? These types of description. I'm going to replace this R by a what? A noiseless resistor. This R is a what? No, bless you. Noiseless. These were two big ones. Noiseless resistor. Just joking, just joking. This noiseless resistor in series with a voltage source. And that voltage source, we will call it what? Vn, which is what? Noise voltage. This is called the Thevenin. Are you familiar with Thevenin? This is the Thevenin equivalent of this. Or I can represent it by what? A current source in what? In parallel with a resistor. Are you following? And this one is what? IN. Clear? Clear? Okay. This again is what? Is noiseless. Because you took the effect of the noise in here. Clear? Now, the Vn square of T bar. What is this called? Anybody? What do I call this? This is called, first of all, do you understand what this means? Average. And this one is what? Square. So this is called what? The mean square value. What does it represent? Okay, first of all, tell me what is this? Assuming the noise is what? Gaussian? Yes or no? Cannot hear you. What is this? What am I calculating? Average. What is the average of noise? Most of the time you model it as what? Average is what? See. You have seen noise in the oscilloscope. Have you seen noise on an oscilloscope? Somewhere down the line. That's in the when you were in your undergraduate. Yes? What does it look? Fluctuations. Very fast fluctuations in time. Why? Why is it very fast fluctuation in time? What did we saw the spectral density, power spectral density of the noise look like? It looks like what? Constant for what? All frequencies, which means what? High frequencies are there or not there? There. Yes or no? So when you look at it in the oscilloscope, which is the time domain description, you will see what? And you see some of it are what? Positive. Some of them are what? Negative. What is the average? See. Did you get this or not? What does this represent? The mean square value. What does it represent? This is called what? The average represent the average noise power generated by R. Clear? Clear? Now they found that this, by the way, you can also write it like this. Either this or this, same thing. Here, same thing. Clear? They found it equal to 4 K T B R. I need you to explain to you what this is all about. First of all, R is the what? Resistance. B is what is known as what? The noise bandwidth. I will explain this one to you in just a second. The noise bandwidth. T is the what? Temperature. Clear? K, anybody? Very good. That's the Boltzmann
The time is 2 o'clock.
constant. Clear so far? Clear so far? Now, this is the what? This is the noise power generated by what? By R. I would like to find what is the noise power that is delivered to the load. To the load. This is not the load. This is the source. Did you get this or not? This is the source of what? Of the noise. So now what I have is the following. This is what? R. Yes? Associated with a what? This is what? Notice, by the way, what is the voltage? If this is the power, what is the voltage? The voltage is what? Square root. Are you following me or not? Okay, but I'm writing it as a power source. Clear? Okay. This is the source. Did you get this or not? Yes or no? And I'm going to add a load. What is the worst case scenario? The noise power delivered to the load. The worst case scenario. You take the worst case scenario, not the best case scenario. You follow me or not? Let me ask you a question. What is the best case scenario? This R equal to what? If it is 0, it means what? Short circuit. I think you meant what? Open circuit. I think you meant open circuit. Open circuit means what? There is no current in here. Are you following me? So there is no noise. Did you get my point or not? It's open circuit. Yes? What is the worst case scenario? The worst case scenario, which is what? The maximum power transfer. Maximum for a signal, by the way. Is that what I look for? For the signal, for the desired signal. Is that what I look for? I look for the maximum power transfer. I don't want to what? I don't want the power to be what? Reflected back because of the mismatch. We'll talk about impedance matching shortly. Did you understand what I just said or not? But for the noise, I also need to assume that the load is what? Is matched to the what? To the source. Yes? So what do I have here? R. That's a load matched to the what? Source. Did you get this or not? Okay. What is the power? What is the noise power? What is the noise power? Delivered to the load. Still waiting. Hey, one second. Okay. Is this behaving as a voltage division circuit? It's behaving as a voltage division circuit. What is the voltage here? This point. What is the voltage? The voltage is what? Is this voltage, not the power, the voltage. Yes? Divided by what? R over what? 2R. Yes or no? In other words, it's what? Square root of what? 4 K T B R, yes or no, R over what? 2R. Yes? What is this so far? So far, what is this? That's the voltage across the load. Then what? Square divided by what? R. Why is it not 2R? Why is it not 2R like we saw in the case of the signal? The signal is sinusoidal. Are you following me or not? This is not a sinusoidal. It's a random signal. You lost me here. Did you lose me? Hey, you lost me. Hey, I lost me. Well, let's assume I have A cosine omega naught T across an R. What is the average power? It's A square over what? Do you answer where the two came from? Because this sinusoidal. Is this one sinusoidal? It's not sinusoidal. So it's what? It's the voltage square divided by what? R. This one is already averaged. Did you get this or not? So what do I get? What do I get? This cancels with this. This becomes what? 4 will cancel with this 4. Yes or no? And the R will cancel with this R. Why? Because this one is square. So what do I end up with? K T B. Units. What do you notice? What do you notice in this expression? It's independent of who? Of the R. This one is independent on the value of what? R. As long as the load is matched to the what? Source. As long as the load is matched to the source, I don't care about what? The value of R. The value of R will cancel out. Did you understand that or not? Yes or no? Cannot hear you. Now what do you see here? That it is a function of what? The temperature, which means what? The Boltzmann constant is constant. That's why we call it a Boltzmann constant. So it depends on what? T, which means what? The higher the temperature, the noise power will also what? Increase the noise bandwidth. The wider the bandwidth, more noise will what? Get in. Yes? Let's talk about the bandwidth for a minute. But did you get this? Okay, let me ask you another question before we get to the bandwidth. Let me ask you a question. I have two resistances in series. This is R1 and this is what? R2. Two resistances in series. Both of them introduces what? Noise. Yes? What is the model? What do I model them? Look what I modeled them. R1, which is what? Noiseless. In series with a what? Again, is this a voltage source or is it a power source? This is a power source. Keep that in mind because I'm squaring. If it is a volt source, you need to take what? Square root. Yes or no? Okay. And then what? R2. Yes? Again, it's noiseless. What is this? Sorry. Clear so far? Yes or no? Okay, how do I model the equivalent? What do I do? Remember, this is a power, this is a what? Power source. Clear? Okay. If the what? If the two noise sources are uncorrelated and hence what? Independent because what? Because they are what? Gaussian. This is again EE 503. Listen, don't worry about it. Don't get scared if you did not take 503. Don't get scared. What I'm trying to tell you, have you taken any course in probability? How many of you have not taken any class in probability? Never. Never? Undergrad, that's not never. Never means what? Means never. Okay. If the random variable, which one is stronger? Listen to me. If I tell you two random, I don't want to get into random variables, so I'm going to ask you one question only. But once I get to the random variables, you lose me completely. So just answer me the following question. If I tell you that two random variables are independent, are they uncorrelated? They are uncorrelated. Are you following me or not? The correlation is a measure of the linear dependency between the two random variables. Linear dependency. If I tell you the two random variables are independent, what does it mean? There is no relationship between them, whether linear relationship or otherwise. Did you get my point or not? If I tell you two random variables are independent, are they uncorrelated? They are uncorrelated. If I tell you two random variables are uncorrelated, are they necessarily independent? No. They could be what? There could be a relationship between them, which is what? Nonlinear. Yes? However, if they are Gaussian, if those two random variables are Gaussian, jointly Gaussian, then if they are uncorrelated, they are automatically what? Independent. Did you understand that or not? Cannot hear you. What is the equivalent? Give me the equivalent. How would you model this? This is how you model. R1 plus what? R2. And what is this? Vn square of t, which is equal to what? Vn 1 of t square plus what? Vn 2 of t square, which means what did I do to the powers? What did I do to the powers? I added them together. Did you understand what I just said? If they are, who's they? Who's they? The noise sources. Noise source. If they are correlated with a correlation coefficient, rho is, by the way, is between what? 1 and minus 1. Sorry. Between what? 1 and minus 1. Yes or no? Cannot hear you. How do I model? R1. Yes? Look what I'm going to do here. No. Did you get my point? Yes or no? Yes or no? Okay, what does that mean? What does that mean? Let me explain to you what does that mean. You are adding what? Voltages, and then what? Square the whole thing. Let's assume rho is equal to 1. Assume, just for simplicity, assume rho equal to what? 1. So that you don't have to worry about it. Rho 1 means what? Total linear dependence. Then what do you have? You have Vn1 of t plus Vn2 of t. The whole thing, what? Square. And then what? Average. Which means what? The first one, square, will give you the what? Will give you this term. You agree? The second one square will give you this term, but there is a what? There is a middle term. Are you following that? You need to take the middle term into consideration. Now, most of the time we are going to assume that they are what? Uncorrelated. Clear so far? Yes or no? Okay, good. Now, let's get a little bit to the bandwidth situation. So, the noise, bandwidth. Now, first of all, let me review something. Recall. I have a system with a what? What is h of omega? What is h of omega called? Frequent? No, don't call it the transfer function, please. Call it the what? Frequency response. When you use the transfer function, it means what? H of S, Laplace. Who said transfer function? Don't use transfer function. Transfer function is what? H of S. Use the what? Frequency response. Yes? Okay. This is the what? This is noise input, N of T. This is what? Noise output, N of T, and 0 of T. Yes or no? No response. Yes or no? Okay, let's see if you can help me. S, N, 0 of omega. What is this in words? Before you tell me the equation, can you tell me what is it in words? Is the power spectrum density of what? The output noise. Measured in what? Units. Watts per hertz. And what is another way of saying watts per hertz? Joules. It's the same as joules, but nobody uses the word joules. They use what? Watts per hertz. Did you get this or not? But keep in mind, the watts per hertz is a measure of what? Energy. Clear? Okay. What is SNI of omega? Same thing, but it's what? Input noise. Clear so far? What is the relationship between them? S, N, 0 of omega. I'm still waiting. Cannot hear you. S, N, I of omega times the at the beginning you did not say the absolute value. Did you say the absolute value? That's why I hesitated. I froze. I froze. When I hesitate means what? I froze. The absolute value of what? H of omega square. Did you get it or not? If you do not put the absolute value, H of omega is in general a what? A complex function of omega. Did you get this or not? Yes or no? I will show you that in just a second. Now keep in mind, H of omega is equal to what? Absolute value of H of omega times what? E to the J, the phase of H of omega. This we call it what? What do we call it? The magnitude, response. This one we call it the what? The phase response. Question. Do you see the phase response here? What does that tell you? It tells you that what? That when you deal with power measurement, the phase response does not get into the what? Does not get into the picture. Only the magnitude response. Clear? Clear? Okay. What is the power? What is the noise power? What is the noise power? At what? Output. Still waiting. The noise power, not the power spectral density. The noise power, still waiting, is the integral minus infinity to infinity SNI of W times what? D omega. Did you get it? Yes or no? Cannot hear you. Which means what? What is the noise power? Remember, this whole thing is what? S, N, 0 of what? Omega. Which means what? The noise power is the area under the what? The power spectral density. Did you get this or not? Yes or no? Question. Why did I integrate from minus infinity to infinity? Because I'm assuming that h of omega is what? Extend from where? Minus infinity to infinity. Yes or no? That will lead me to what is known as what? Noise equivalent bandwidth. B. This B is this B in this equation. Which equation? Which is this equation? Did you get this or not? What do? You use a what? A brick wall filter. What do I call this filter? This is Bn minus Bn. Question, what do I call this filter? An ideal low-pass filter. This is an ideal low-pass filter. Did you get my point or not so far? Yes or no? Okay, can I realize this? Realize means what? Can I build it? No, I cannot build it. Why? Because if you take the what? The inverse Fourier transform, you will get a what? A filter which is what? Non-causal. Non-causal is not allowed. Sorry, not allowed. You cannot build it. Yes? Okay. What is this am I sketching? Tell me, what am I sketching now? That's the actual what? Filter. For example, a low-pass filter looks like what? Looks like R, C, yes or no? And what is h of omega? H of omega is what? Yes or no? And what is the, are you following me or you are losing me? Okay, and what is absolute value of h of omega? Clear? No square root. Why? Because I already squared it in here. Did you get this or not? How would you sketch this? How would you sketch it? This one. Yes or no? Cannot hear you. Okay. Where is the power? The actual noise power. The actual noise power is this. Yes or no? Cannot hear you. What is the power if we use the ideal low-pass filter? Is this. Are you following me or not? Let me ask. I'm not sure you followed me. Did you follow me or you lost me? I want you to see these two regions, this one and this one. Are they included in the practical filter? This one and this one. Yes? Which means what? I want you to see this. If you only take this, which one has a higher power? The brick wall or the actual filter? The brick wall has more. But when you add these, yes, to be for both of them to be the same is what? Over which, now let me ask a question. The wider this brick wall, the wider it is, does it have more additional than this? Within the band of interest? Yes or no? After you increase those, after you add those to this, yes? When the noise power under the what? The practical filter is equal to the noise power under what? The ideal filter, what is the noise power under the ideal filter? Under the ideal filter, what is it? It's what? Is this value, yes? Okay, multiplied by what? 2Bn. When you calculate the power, you need to what? You need to take both the negative and the positive. Yes or no? When the power, when? Did you lose me? Did you lose me? You lost me. When the noise power that passes through the actual filter is equal to the noise power that passes. That passes through a brick filter of bandwidth. What is the bandwidth of the filter? Bn, not 2Bn, Bn. Clear? Let's see if you can help me. Let's see if you can help me. Assume the input noise is white. What does it mean? When I say it's white, what does it mean? Sni of omega is equal to what? N0/2. You have seen this before, yes? For what? Agree? Agree? Cannot hear you. Okay, what is the output power? Output power from actual filter. I'm still waiting. What is it? Integral. N0/2 from where to where? Yes? Times what? Agree? Yes or no? Which is equal to what? I'm not sure. Did you follow me? Did you follow me? Which is equal to what? Now, is this symmetric? Absolute value. Is it even function? Which means what? Can I multiply by 2, integrate from 0 to infinity? So what do I have? 2, 0 to infinity, N0/2 times what? Yes or no? Cannot hear you. Okay. What is the noise power? Noise power at what? Output of the what? Brick wall. Still waiting. It's what? It's N0/2, yes or no, times what? 2Bn. Are you following me so far or not? Yes or no? Times what? Listen to this. Why? Can you tell me why? First of all, is there an integration? Is there integration here? There is no integration. Why? Because this guy is what? It's constant. Yes or no? What is the maximum? The maximum of this is the same as the maximum of this guy. Yes or no? I square it. I N0/2. You lost me here? You did. Okay, you did. First of all, where did this come from? When you calculate the power, you need to take the positive and the what? Negative. So do you understand this? Okay, what is this? This is the power spectral density of the what? Of the input. Yes or no? Just like this one. Yes? What is the difference between this one and this one? The difference between this one is that I integrated the absolute value of h of omega because this one is not constant. And this one is constant. Yes or no? You lost me here. Let me rewrite this in a different way. Let me rewrite this. What is it? N0/2, the integral, minus Bn to what? Bn, absolute value of what? D omega. Do you agree? Do you agree? Why is this one? Is this constant? Can I get it outside? What remains? Integral of d omega. This is constant.
Professor, you have 5 minutes left.
This one is constant. Do you agree? Yes or no? This constant. Can I get it outside? What remains? Integral of d omega between what and what? Minus Bn to what? That's it to Bn. And this is the N0/2, and this one is a constant. Yes? When this power equal to this power, when 1 equal to what? 2, what do I have? Tell me, what do I have? Okay, the N0/2 will cancel this with this N0/2. Do you agree? This will cancel with this. Do you agree? So what is Bn? Give it to me. I'm still waiting. Here, one more time. I am equating this with this. The N0 over 2 cancels. Agree? The 2 cancels. So what is the Bn? Bn is from 0 to infinity, absolute value of what? Yes? Divided by what? The absolute value of h of omega max square. No integration here. In the denominator, there is no integration. That is called the what? The noise equivalent bandwidth. Clear? Yes or no? And is this bandwidth that you are going to plug here? Clear so far? Yes or no? Okay, good. Now, next term. Next thing, which I will discuss next time. Are you following me so far or not? Okay, next thing, which is the what? The noise figure. Let's understand what a noise figure means. They brought a device. This is a device. Clear? Okay, they called what, by the way, in the literature, I will show you. This is in later. They call it DUT. What does DUT stands for? Device under what? Testing. You are testing this device. They apply a signal here, and they look at the signal in here. And this is a what? An amplifier. Yes? They said the following. Listen to what they said. They said that this amplification, the signal to noise ratio, power ratio here should be the same as the signal to noise ratio power here. Why? Because the amplifier is going to amplify both the signal and the noise. You follow me or not? So they started measuring. They measured the signal to noise ratio at the input and the signal to noise ratio at the output, and they found it to be what? Not equal. They found it to be different. I'm not sure, did you get my point? Did you get my point or not? They found it to be different, which means what? The only explanation to this phenomenon is what? Is that this device introduced what? Internal noise. Are you following me or not? So they needed to quantify it. They needed to quantify this. They defined a noise figure, NF, which is equal to what? 10 log. Why is it 10? Why is it 10? Power ratio, 10. The signal to noise ratio at the input divided by the signal to noise ratio at what? Output. Now, this is, they call it noise figure. And if you define it as F is what? SNRI over what? SNRO. This one they call the what? Noise factor. And of course, this one is much more widely used than this one. Clear? Now listen to me. There was a controversy in this definition. What was the controversy? They needed to fix the temperature. Why? Why? The signal to the noise power, as I showed you a moment ago, does it depend on the temperature? They did not want to define a noise figure and tell you this is the noise figure when the temperature is this. This is the noise figure when the temperature is what? This. They wanted a what? A universal measure. Are you following that for the noise figure? Regardless of what? What is the temperature? Are you following me or not? So this is what? This definition. Let me write this and then we'll continue next time. This definition applies at what? Room temperature only. Are you following me or not? And that room temperature is designated by T sub 0, which is equal to what? Roughly 290 Kelvin. Did you get this or not? Where is this K? Where is this K? Tell me. Did you get my point or not? Did you get my point or not?
Professor, we're out of time.
Yeah. We'll continue this next time. But did you understand why? They did not want different noise figure for different what? Temperature. They wanted just a universal definition. Clear? But we'll continue next time. Did you follow me? Okay, we'll continue next time.
This concludes today's session of ED 544 on Tuesday, February 11, 2014.